So let's go through the same routine, but with cosine. So working with our original cosine function, that's where we were given some angle measurement. And then what we would find is the x-coordinate on our unit circle. Or if we were looking at a triangle, it was our ratio of adjacent over hypotenuse. So the input for this is an angle measurement, and the output was that x-coordinate. So where sine worked with the y-coordinate, we're working with x here. Or if we look at a right triangle, it's that ratio of adjacent over hypotenuse. So when we go to our inverse function, so this is inverse of cosine, and you can use either notation with a -1 or arc cosine. They mean the same thing. We're just going to switch what our input and output are. So now the input for this function, what we'll see inside of the parentheses, is an x-coordinate on the y-axis, or in that ratio of adjacent over hypotenuse. And then the output for the function is going to be the angle measurement that lines up with it. Okay, so similar to what we talked about with sine, we looked at cases where we could be solving and maybe we knew what the x-coordinate was, but we didn't know what the angle measurement was. And when we worked with those cases, the idea was that there were two possible solutions for each location, and we can't have that happen. So this is where we're going to restrict the domain so that we know what kind of window we're working within, so that we don't end up with too many solutions when with a function there should only be one solution. All right, so let's say I start at x equals 0, so an angle measurement of 0. So I'm going to start right here at the peak. And I'm going to move to the right-hand side. So as I move along here, I have all unique y values, unique y, unique, until I reach right there. If I go any further beyond that, we would fail the horizontal line test. Similarly, up here, if I move to the left at all, I would fail the horizontal line test. So I need to work within this window from 0 of an angle measurement to pi. That's going to be our limitation on our angle measurements. So something to note is that this restriction is different from sine, so we'll need to pay attention to what function we're working with to know which angle measurements we're allowing. So what we could say is that we calculate arc cosine or inverse sine. We calculate inverse cosine, only for angles between 0 and including those endpoints and pi. So visually what that looks like on our unit circle is we're stuck in the first and second quadrant. And as we can see here, I didn't really show that with sine, but we can see we have all of these unique x coordinates. We can see everything from +1 to -1 coming through here. And then we're just not allowing the repeats that come through down below. It was the same thing for sine in the last video. I just didn't kind of highlight that, is that we have all of our unique y coordinates in there. It's just we're not allowing the repeats that are coming through on the other side. All right, so let's get some practice with solving with these. So again, I'll make that little note that √3/2 and 1/2 are going to relate to increments of pi/6. √2/2 is going to relate to increments of pi/4. So, inverse cosine. if I start to draw my picture, well, actually, sorry, let me write in wording what we're looking for here. So we're looking for an angle measurement. So we're trying to find an angle where this is our x coordinate. So x is equal to √3/2. So with that, I can start to get a visual going. And with my unit circle, I can only be, since we're working with inverse cosine, we can only be in the first and second quadrant. Now, something we know is that x is positive. So oh, sorry, I didn't want to draw it there. We're going to be in the first quadrant. So we have to be on that part of the graph because x is positive. Over here in the second quadrant, we have all of our negative x values. Now negative √3/2, so that's going to relate to an increment of pi/6. And this will be the case where x is long, and that's going to come through right here. Ooh, not the straightest line, but something like that. That's where we have a coordinate of √3/2 and positive 1/2. Sorry, my angles are a little off there, but close enough. So that measurement, we go from standard position up to that value, and that's a pi/6. So this inverse cosine of √3/2 is equal to that angle measurement, which is positive pi/6. Again, we could check that with the calculator. Just plug in this inverse cosine of √3/2 and then check it with the decimal form of pi/6, and they should be exactly equal to each other. And then where this is our solution, you can see it in a similar format. We could switch back to our original cosine function where the input was the angle measurement. So that was a case where we would draw pi/6 as our angle and figure out the x coordinate, and that would have that x coordinate of √3/2. So these are explaining the same situation, just in two different forms. Here we knew our x coordinate and we're finding an angle, and here we knew the angle measurement and we're looking for the x coordinate. All right, one more example here. So this one, it's inverse, so we're looking to find an angle measurement where we have an x coordinate, since we're looking at cosine, of negative √2/2. So if I draw my picture here, and we're only looking from 0 to pi, and my x coordinate is negative, so that tells me I'm going to be over here in the second quadrant where I have all my negative x coordinates. So negative √2/2 is going to relate to a pi/4. Just going to be there. So let's see, that's the coordinate, and we don't really need to write the coordinate, but I just kind of like to write it out to double check. So x is a negative √2/2, and then y is a positive √2/2. And then in terms of angle measurement, I have 1 pi/4, 2 pi/4, 3 pi/4. So we're within that range of 0 to pi, so we measured that correctly. With this, it's kind of hard to get outside of that range by going like in that direction. Would be kind of strange for us. With sine, it's just a little more tricky because we had been used to kind of going all the way around to the fourth quadrant. And with sine, we're doing this going in the negative direction. But with cosine, it's not too bad because it's mostly, or not even mostly, it's always going in that positive direction. All right, so this inverse cosine of negative √2/2 is equal to that angle measurement of 3 pi/4. And let's just go ahead and take a look at the calculator there, just to show you how to check it. So inverse cosine of negative √2/2 is equal to all of that. And what we found was that that angle measurement, what was it, 3 pi/4? Same exact thing. So because those line up, we're all good to go. All right, so that's our inverse cosine. So it really operates this very similarly to the inverse of sine. What's just changing is the kind of range of angle measurements that we're allowing for our outputs is 0 to pi instead of negative pi over 2 to positive pi over 2.